Mosaic is a middle-tier architecture that orchestrates data views and backing databases, unifying scalable visualization techniques within visualization languages. Now, after decades of visualization library and language development, I think it's fair if your initial response is, yet another visualization toolkit? However, we contend that open source visualization tools still suffer from a lack of scalability and flexibility. Our tools should scale to the large data sets now common across science and industry. Tools should leverage modern analytical databases to manage large data volumes efficiently, should apply specific local optimizations when chart semantics are known, and apply more general optimizations to reduce interactive latency. At the same time, our tools should be flexible and interoperable. Scalability optimization should be provided automatically. Linked interactions should be supported, not only among visualizations, but also across various visualization libraries. And tools should be usable within computational notebooks and on the web, with or without a backing database server. Mosaic is our attempt to support these goals, using an architectural layer between backing data sources and interface components. Here we use Mosaic to explore 1.8 billion stars in the Gaia catalog. Selecting higher parallax stars reveals the main sequence of stellar lifespans in the plot of color versus brightness on the right. We can trace this sequence to see how the stars distribute in the sky map on the left. The distribution appears relatively uniform until we brush down to the brightest stars. Mosaic provides a standardized selection abstraction for linking across tables, visualizations, and input widgets such as sliders, search boxes, and menus. All of these components are linked via dynamic parameters and coordinated queries. Computation of regression models, interquartile ranges, and other transformations are automatically pushed down to the database. Meanwhile, the table component prefetches data to ensure smooth scrolling. A Mosaic application consists of data-driven clients that publish their data needs as declarative queries. The Mosaic coordinator manages these requests and submits queries to a backing database. By default, we use DuckDB, a scalable open source database that can run locally or in a browser via WebAssembly. Query results are returned to clients for rendering. To transport data, we use Apache Arrow, a binary format that enables efficient transfer with no subsequent parsing overhead. The coordinator caches query results for faster responses to repeated queries. Mosaic also mediates linked interactions. Updates from clients or interactors populate dynamic parameters such as selections, which manage multiple filtering predicates. Selections resolve updates across multiple clients, supporting techniques such as cross-filtered views. To assess Mosaic, we developed VGplot, a grammar of interactive graphics. In VGplot, each mark is a Mosaic client that generates queries. We use observable plot to render query results to scalable vector graphics. For example, we can create this chart using an area Y mark. A basic query selects all data points, here resulting in 50,000 rows. In Mosaic, the area mark instead applies M4 optimization, performing pixel-aware binning to reduce the data by over an order of magnitude. This is an example of a local optimization based on known semantics of the visualized data. Now let's create an overview plus detail interaction. We duplicate the area chart and then coordinate charts with a selection. The top chart includes an interval interactor to filter the bottom chart. We can now explore the data with both M4 and caching optimizations applied on every update. Here we visualize 10 million flight records as histograms. We bin along the x-axis and visualize counts per bin on the y-axis. We add a selection with cross-filter resolution and add interval brush interactors. And as we select longer and longer arrival delays, we see those flights are more likely to leave later in the day. And rather than requery the full backing table on each update, the Mosaic coordinator analyzes queries to automatically generate data cube indexes, here binning over all pixels the brush endpoints might occupy to pre-compute aggregate results. Then on each update, we instead query the pre-aggregated data cubes, providing substantial speedups. To evaluate scalability, we conducted performance benchmarks, comparing Mosaic variants to Vega, Vega Fusion, and observable plot. Mosaic provides order of magnitude improvements for the initial rendering of aggregated bars, linear regression plots, two-dimensional histograms, and area charts. Other tools fail to render area charts with millions of points. Mosaic also provides superior performance for density contours and hexagonal bins. These performance improvements for static visualizations arise primarily from the use of DuckDB as well as local optimizations. The local DuckDB server outperforms WebAssembly thanks to higher parallelism. We evaluate interactive performance on real-world datasets ranging from millions to billions of records, including the flight delay and Gaia star catalog examples seen earlier. Data tile indexes can be built on the fly for up to hundreds of millions of points, but beyond that, pre-computation is desirable. With indexes in place, Mosaic supports real-time interactive updates, even between high-resolution raster visualizations. Vega Fusion is not competitive due to its lack of indexing. And prior indexing systems, such as Immense and Falcon, also fail at this scale, as they involve dense indices that grow too large for main memory. Mosaic's use of sparse indexes, hosted in database, preserve highly scalable interactions. Moreover, Mosaic provides these optimizations automatically via query analysis. Mosaic applications can be specified in a portable declarative format, enabling rich integration with environments such as Jupyter Notebooks. Here, DuckDB runs in the Notebook's Python kernel and can also access Python data tables with Mosaic visualizations accessible as Jupyter widgets. While low-level libraries like D3 can be used directly to author Mosaic clients, important future work involves developing new tools and integrations. This proof of concept example shows Mosaic-mediated linking between Vega Lite and VGplot views. Mosaic also opens up multiple future research directions. Mosaic includes logging mechanisms that can be used for empirical studies of user behavior and query workloads. And the results can inform new optimizations, such as novel indexing or approximation techniques, or cache eviction policies that explicitly account for latency. And by mediating between client requests and query evaluation, Mosaic could support dynamic deployments in which computation and indices are moved between server and clients based on available resources. In conclusion, Mosaic supports expressive, extensible, and interoperable data views that compose diverse visualization, interaction, and optimization techniques. Mosaic's middle-tier architecture coordinates link selections among views while providing automatic query optimizations. Mosaic clients communicate their data needs as declarative queries, while the central coordinator manages and optimizes these queries. Mosaic unifies the abstractions of popular visualization toolkits with scalable visualization techniques. The Mosaic coordinator optimizes over multiple views and interaction cycles, including automatic application of novel data cube indexing methods. We also demonstrated order of magnitude improvements over existing web-based tools. The Mosaic architecture, query helpers, VGplot, and input widgets are all available online as open source software. We hope Mosaic can serve as a promising open source platform for the research and development of scalable interactive data systems.